Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and privilege to be serving you today, as it is every day, here in my virtual classroom. Step one aside as you have reached the end of Chapter 11 with the Chapter 11 Tests and Cumulative Assessment in the Big Ideas Math Integrated Math 2 textbook. This is probably the last section we do in general out of the textbook as a whole, so congrats for reaching that end at least, and let's see what you can do with this. 15 problems out of the Chapter 11 test, 9 problems out of the Cumulative Assessment. Download the PDF below if you'd like to find either of those things and find the timestamps for each specific section and those problems, and grab a calculator, I'm sure, as we do things on circumference, areas, and volume. Let's dive right into this, shall we? And let's see how long or short this goes. Numbers 1 through 3, we tell whether the solid is a polyhedron if it is named a polyhedron. If it's not, I'm still going to try and find some name for it. So number 1, not a polyhedron. Number 1, not a polyhedron because it contains a non-polygonal base. Polyhedron. A non-polygonal base in that quarter circle. In fact, I'm sure if you wanted to call this something, you could call it a quarter cylinder, as there is a semi-cylinder, I suppose. So quarter cylinder would be some other name for it. They're not asking you to name this. I'm just doing it for you. They ask you to name it if it is a polyhedron, and we're going to make sure to do exactly that. Let's take a look at number 2 with that in mind. Number 2 will be a polyhedron. Everything is some sort of polygon. All the lateral faces are triangles, and at the bottom there, you have a 1, 2, 3, 4, 5, 6, 7, 8-sided shape. That is an octagon. This is a pyramid. This is a polyhedron and an octagonal pyramid. Octagonal pyramid is that name. Now, these names are important when it comes to calculating volumes and surface areas. Knowing the fact that it is an octagon means when you find its area, you're going to do something specific to octagons, and that it's a pyramid. It's the 1/3 area of base times height for volume. And we didn't actually do surface areas of pyramids for this stuff. Save that for IM3. We did them for prism. No, excuse me. We didn't. We did them for volumes for these. Number 3 is as well a polyhedron, as it has all rectangular lateral faces and pentagonal bases. This is a prism, a pentagonal prism is the name. So prisms have 2 bases which are congruent to each other and parallel to one another, having rectangle or parallelogram, if oblique, lateral faces meeting up to them as they stay parallel like that. And we can calculate their volumes like we will do on numbers 4 through 7, find the volume of the solid. So the first one, number 4, knowing its name is once again going to be important for what we do. This is a hexagonal prism. 6-sided shape, bases on top and bottom. And they don't have to be the top and bottom, but they do have to be the bases. So on top and bottom, the bases are hexagons. We have to find, for volume, area of base times height. So we got to find the area of that base. This hexagon being this whole 1/2 apothem times perimeter thing goes on. So in this bottom of the hexagon, I'm not going to draw the whole thing. We need to figure out the apothem, the distance from the center perpendicularly to the shortest distance to the side, like that. And all we know on this thing is we have an 8 meters. Now, it's a regular hexagon. It's 8 meters all the way around. This apothem bisects the side, making this 4 meters. And that's important because in this right triangle, we can find the apothem by knowing how the central angle here of 60 degrees, 360 over 6 being a hexagon, divides by 2, and we get 30 degrees for just this guy right here. So as I wrote all that, I'm going to delete all that and just place this as 30 degrees. So this is a 30, 60, 90 triangle. Opposite the shortest side, opposite 30 is the shortest side 4. Opposite the 60 would be root 3 times larger. The apothem is 4 root 3. I should preface this by stating if this is your first time seeing any of this information, you're probably not going to get a lot of it. This is a chapter test kind of review thing if you're watching it as a solution guide, so it's expected that you know a little bit about what I'm talking about at this point. I'm talking about what I'm doing, maybe not so much the teaching aspects of it. The perimeter is going to be, it's a regular hexagon, so 8 times 6, and we get 48 meters for that. So the area of the base as a whole will be 1/2 the apothem times the perimeter. Half of 4 is 2. 2 times 48 is 96. We get 96 root 3 square meters for the area of the base, either of those hexagons. Times the height. This height is, I'll just write it here, The height is 15.5 meters. So I'm definitely going to be going to the calculator for this guy right here to calculate that whole area of base times height bit and get prepared for that. Volume, area of base, times height gives me something. 96. Let's just do 96 times 15.5 first, just to get you an exact looking answer. 1488 root 3. 1488 root 3 cubic meters. And that rounds to, when you multiply by root 3, normally we're doing nearest hundredth stuff. Root 3. 2577.29. 2577.29 cubic meters. That's the volume of this prism for number 4. Number 5, the volume of this sphere. A sphere's volume formula is volume equals 4/3 pi r cubed. So we need the radius. In this sphere, you have a diameter of 3.2 feet. So the radius will be half of that, which is 1.6 feet. As the volume is 4/3 pi r cubed, we are going to take 1.6 and cube it, multiply by 4/3, divide by pi, all that kind of stuff. So I'm going straight to the calculator for that. I can't imagine any of this would be very clean looking ultimately. So times 4 divided by 3 times pi. We're getting 17.16, one rounded. It's 157. 17.16, what are the unit? Feet? Cubic feet for volume of this sphere. Number 6. We have a composite solid. Number 7 will be also a composite solid. And this has 2 cones on top and bottom, both congruent, I suppose. So whatever the volume of one of the cones is, we'll go ahead and double it. In the middle, we have what's called an oblique cylinder. It'll have the same volume as a normal cylinder thanks to, what's his name? Cavaliere's rule or something like that? The Cavaliere's principle, I believe, that kind of states that. But anyway, as long as you're referring to the height as the perpendicular distance between your bases, the 6 meters will be very specific for that one. So let's consider this to be object 1, and object 2 I'll be doubling ultimately. But let's start with the cylinder portion. The volume of a cylinder is area of base times height, just like it was for volume of a prism. Now the area of base in this case, I'm just going to write that to start with. The area of the base, well, it's going to be the area of either of the other bases for the cone. So I'm just going to leave that like this, but I'll call this height 1 here. The area of any of the bases here for these circles is pi r squared. Radius is 4. We get 16 pi square meters. Now the height of object 1 is 6 meters. It is the perpendicular distance here. It doesn't matter if it's oblique or not. So the volume of object 1 will be area of base times height, which is 96 pi. Let's just leave it like that for now. That's in cubic meters. We'll do the rounding later when we figure out volume 2. We double it and we add it to the total. Now, these are cones. Volume of a cone is 1/3 area of base times height. They have their own separate height. I mean, each cone has the same height, but it's separate from the cylinder's height. So height of object 2 is 4 meters for either of those. The base area is still the same. They're still using the same circle as before, but we take the 1/3 when it comes to a cone. 1/3 that of what a cylinder would have, I suppose. So the volume of object 2 is 1/3 of 16 pi times 4. Now that's 64 pi over 3 cubic meters. Still no rounding just yet. We'll get to there. Here's the thing, though. We got to double that volume because there are 2 cones. So I could have put 2/3, this whole time. Work that out. But that's okay. So the volume of the total of this whole composite solid will be doing the volume of the cylinder plus 2 cone volumes. So we are going to get 96 pi plus 2 times 64 pi over 3. And again, if we want to work exact, we can probably do some of that to begin with. 96, let's do this. 96 times 3 is 288. So 288 thirds pi plus, and this would be 128 thirds pi. And that'll give you, 416 thirds pi. This is something where I feel like if I'm working too exactly, I'm probably going to mess something up, and I might have because I did that all kind of, without a calculator. Let's try and make sure that works out. 96 times 3 is 288. 28 plus 128 is 416. Okay, so I'm trusting that for myself that everything else worked with that. Multiply it by pi, divided by 3. It'll be somewhere still close to 416 because pi isn't much more than 3. 435.63. So 435.63 cubic meters of volume as a whole. So we took the volume of the cylinder, added 2 of those cone volumes as they're both congruent to each other, and doubled it. And there we go. All right, let's move on to number 7, the last composite solid that we have, and probably the last one we're finding the volume of, at least for a while. Trying to think what sections. Do they say what sections these are out of? No. These have been out of anything from sections 11, because I didn't say any of the sections yet. I forget where we ended on some parts, like 11, 4, 5, 6, something like that. Can't remember specifically anymore. All right, so number 7. We have 2 objects here. We have a rectangular prism on bottom, and we have a rectangular pyramid on top. I know they're rectangles because if I refer to these as bases, I'm probably going to, considering this would share that same base. That's a 5x2. That's a rectangle. Everything there's a rectangle on the bottom. The top has some triangles making it a pyramid. So, object 1, we're going to do area of base times height. In order to get there, let me back this up a little bit. Area of base for both objects is 5 times 2, which is 10. 10 square feet of base area. The height of object 1, based on how I drew that, is going to be 8 feet. So, the volume of object 1 is area of base times height. 10 times 8. We get 80 cubic feet of volume for object 1. Now, object 2 has same base area, its own height of 4 feet, and it is a pyramid, so we are going to be taking 1/3 of that area of base times height. Area of base being 10, once again, the height being 4, that's 40/3. 40/3 cubic feet, and there aren't 2 of them, there's just 1 of them. I consider 6 to be a trickier problem than 7 all told, but excuse me, we still work it out. So the volume of the total, we add both of those volumes together, we're going to take 80 and the 40/3. As an exact, 80 is 240/3, right, with a common denominator. So 240/3 plus 40/3, which is 280/3. This doesn't get you anywhere. It doesn't divide by 3. 280/3 cubic feet as a whole, as an exact. Rounded, I kind of want to do that on my own. 93.3 repeating, I believe. I'm going to try that, so I'll just put 2 3s if I'm actually doing the rounding. So cubic feet like that. Let's try that. I feel like I'm not wrong. 280/3. Yeah, 93.3 repeating on that guy. So that is the volume of question 7. That composite, that house. Okay, let's move on to numbers 8 through 10 where they find indicated measures. Now, they'll ask for different things. The first one, circumference. Next one, measurement arc, and then area of shaded sector. But they all have the same component going on. You can set up proportions within these things as long as you have the central angle going on and you know what you're referring to, areas or circumferences. On the first one, they're literally asking for circumference and they give you an arc length. So the circumference of circle F is based on the fact that we have a portion of the circumference given the arc length of 64 inches from the 210 degree portion. Now that 210 is a certain fraction out of 360 degrees of the entire circle, same as the 64 inches is out of the entire circumference of your circle. 210 out of 360, I mean, if I do some fraction reduction stuff, I can divide it by 30. I get 7/12. That's not a required bit, but it's easier to say out loud when I work it out. Basically, 64 is 7/12. 64 inches is 7/12 of the entire circumference. If I want to figure out this circumference, I want to take 12/7 of this whole thing. I can cross multiply, divide by 7, the works. Ultimately, you're going to get C equals 12/7 times 64. If you want the algebra in that, once again, you can cross multiply. I'm multiplying C to both sides, 12 to both sides, and then divide both sides by 7 to get C by itself. And I mean, you know, we can work out kind of an exact answer version, but ultimately, if rounding's going to be had, we're going to do that. So 12 times 64, which is 768. We divide that by 7. Whoopsie, I just cleared. 768 divided by 7. And we get 109.6 109.71. So that's rounded. 109.71. This is in inches. This is in inches. That is circumference of the circle rounded. All right, number 9. Measure of arc GH. Same concept. We can set up proportions based off what we have here. Now, the arc is going to be equivalent to central angle. What you saw before, the 210 is central angle. That is also 210 degrees in arc measure. We can measure an arc in its length or in its degrees. And we're trying to find the measure of this thing in degrees, knowing that we have a 35-foot arc length and that we could find the circumference of the entire circle using that radius. So the measure of arc GH is what needs to be found. That arc measure out of 360 degrees is the same as this arc length of that portion of the circle out of the entire circumference of the circle, which we can find by using 2 pi times the radius, 2 pi r. So a little bit of cleaning up to be had. Can't really reduce that fraction, unfortunately. Let's just kind of keep going on this. I'm going to multiply both sides by 360 right now, if that's cool. We'll multiply 360 by basically this. We have 35 over 54 pi. That can't reduce, right? I don't think so. So I'll go straight into it. Once again, I'll use the calculator, and I'm going to go round this however it is. Maybe it's an exact answer. But well, probably not with the pi involved. So 360 times, I want to show you this in my calculator because I do this sometimes when this happens. But 360 times 35 out of, do not just write 54 pi like this. I'll show you, you won't know that it's wrong, but I'll show you the difference in this answer, which is wrong. And you should probably expect that to be wrong. Your arc measure can't be more than 360 degrees, right? But here's the problem. This needs to be in parentheses. Whoopsie. Let me try that again. If you had 54 pi, you need to get this around parentheses. Pi needs to be in the denominator, and this is what's going to make it so. That number makes more sense. This number is less than 360 degrees. It seems like that fraction of the circle is being used up. Around 74 degrees. I'll say 74.27. So 74.27 degrees of arc measure being covered from that arc length given that radius. Number 10. Area of the shaded sector. The shaded sector is in blue. What we do know, we have 2 ways to do this. I'm going to go probably the easier way. What we do know is this central angle is a measure of 105 degrees. This is everything that's not the 105. Now, I'm going to call the, so we'll notice subtract that from 360. I'm going to call the area of the shaded sector X. I think that's just an easier way for me to go about what I write instead of writing area of that region. Anyway, so, whoops, I just hit a button in one hit. Okay, so X. The measure of arc QTR is 360 minus 105. Let's start with that. The degrees that we want out of this thing. So that's 255 degrees. That's the fraction out of 360 that we want for the area of the shaded sector X out of the area of the entire circle. Now that's still something we have to find out. It's not 2 pi r, but it's pi r squared, and our radius is 8. I'm not going to bother reducing this fraction. I think ultimately I can only divide it by 5 anyway. It's not the biggest bummer. But this will turn into 64 pi. So 255 out of 360 equals x out of 64 pi. We got to take 255 3/60ths of 64 pi. We're going to multiply both sides by 64 pi. That's what happens. 255 3/60ths of 64 pi. That's why I reduced that other one to 7/12. That's like an easier fraction. We got to take 7/12 of the number. It's a little cleaner to say. All right, anyway, I'm still going to calculate that one. So 255 out of 360 times 64 pi. We're getting 142.42. That's the area, by the way. 142.42 area. This was in inches. We'll have square inches for that one. The 64 pi was also in square inches, by the way. I could have put that. Okay. Let's move forward to the last 5 of the chapter test portion. Number 11. Find the surface area of a right cone with a diameter of 10 feet and a height of 12 feet. Let's draw out what that looks like. Not number 12, number 11. Let's draw out what that looks like. A right cone is basically an upright cone. We got the party hat. Pardon me. We got the party hat appearance here. And the base, which looks a bit circular-esque. It is a circle. And we know its diameter. What is it? 10 feet. And we know its height. That's the perpendicular one to the apex of 12 feet. For a cone's surface, for a cone's volume, it's 1/3 area base times height. For a cone's surface area, we have to take pi RL plus pi R squared. Now, before I talk about L, let's just start with the area of the base. This is lateral area plus base area. The area of that base, pi R squared, is going to be pi times, well, half of 10, we get 5, right? 5 feet. 5 squared, which is 25 pi square feet. Okay, we have the area of the base. I'll just kind of box it so we know that we have it. That's this guy. Pi RL, well, R is still the radius that we have, 5. L is the slant height. L is this. We need to find this. In order to find this, we can use this cross-sectional right triangle. And I'm probably going to save myself some time when I see that this number's a 5 and this number's a 12, because that, in a Pythagorean triple, would be a 5, 12, 13 triangle. Work out Pythagorean theorem all you want, y'all. This is going to be 13 feet. So you have a 13-foot slant height. That is this one right here. So when it comes to pi RL, the lateral area, we're going to get pi times the radius times the slant height, which is 65. I'm running out of room. Which is 65 pi. 65 pi square feet. Remember, this is all lateral. This is all surface area. There's no cubic units going on in here. This is unfolding this net of this whole thing. So the surface area of the entire thing will be pi RL plus pi R squared. As an exact value, that's 90 pi square feet. As a rounded value, again, teetering toward 300, 280 something probably. 90 pi, 282.74. 282.74 square feet rounded of surface area of that cone. It's a big cone. I don't know where it exists, man, but that's a big cone. All right, number 12, 4 parts. You have a funnel with the dimensions shown. Oh, it's on the right. Okay, you have a funnel with the dimensions shown. I think we're assuming it's just a cone, like an inverted cone, that there's no actual, like, width there that we're referring to. So I hope that's okay. Unless they talk about it. Part A, find the approximate volume of the funnel. Okay, so that's where they say approximate. So they say the cone, it's a cone. So volume of this thing, we do have the radius of 6 centimeters and a height of 10 centimeters. So volume being area of base times height, we need area of base as pi times 6 squared, which is 36 pi square centimeters. So volume, 1/3, excuse me if I just said area of base, 1/3 area of base times height. 1/3 of 36 is 12. 12 times 10 is 120. You get 120 pi cubic centimeters of volume. That's exact. If we have to use it later, I'll be ready to, but if I go ahead and round that thing, 120 pi, what, 375? 120 pi. 376.99, and that is not going to round up. 376.99 cubic centimeters, about. Part B, that's for the funnel. You use the funnel to put oil in a car. Oil flows out of the funnel at a rate of 45 millimeters per second. How long will it take to empty the funnel when it is full of oil? So, by the way, this is where I'm probably going to use the 120 and not the 36.99 because this value is rounded and this value is not. Now, they're telling you that every cubic centimeter is the same as a millimeter. So when they talk about volume, this 376.99, it might as well also be in millimeters, right? 376.99 millimeters. Just kind of getting you ready for that because they use milliliters to talk about this rate of this stuff. It says oil flows out of the funnel at a rate of 45 milliliters. Sorry if I said millimeters. Milliliters per second. How long will it take to empty the funnel? So this is like a whole distance equals rate times time thing. I always like to refer to it in that way. Distance equals rate times time. Distance is volume in this case. The volume that it needs to take to empty is the whole 120 pi cubic centimeters. Now, it leaves at 45 milliliters per second. And this is times some time, which of course would be in seconds in this case. They do say how long does it take to empty. Yeah, we can answer it in seconds. It doesn't say anything about minutes or anything like that. So our answer is going to be in seconds here, right? 120 pi equals 45 t is basically our setup. Right? Now, before I answer it, I'm going to give you a roundabout based off this number being 376. Basically, how many 45s does it take? For every second, it's 45. So 1 second, 45. 2 seconds, 90. 135, 180, 225, 270, 315, 360. This is going to be a little bit more than 360, about a third of the way through there. So it's probably going to be really close to, what was that, 8? About 8 1/3 seconds, because that's about another 15. It's going to be a little more than 8 1/3 seconds is what we're going to get there. So I'm going to go ahead and use my calculator there. We're going to take, we're going to divide by 45. Let's see, t equals 120 pi over 45. If you want to reduce that, go ahead. What is that, 24? Oh, that reduces pretty well. Those divided by 15. That's, what's 15? 8 pi over 3. So let's see what that is. And yeah, that makes sense that that's going to be that number. So 8 pi, because pi is a little more than 3. About 8 1/3, so 8.38. So 8.38 seconds of time. Definitely not going to convert into minutes. No. And that's making sense just as an overall when it comes to getting that. That's part B. Part C. How long would it take to empty a funnel with a radius of 10 centimeters and a height of 6 centimeters if oil flows out of the funnel at a rate of 45 milliliters per second? So they're flip-flopping the radius and the height of this thing. Instead of having what you had before, let's compare volumes. Now this time, volume is going to be 1/3 area of base. I'll just write that as pi r squared times height. Notice the change. We're squaring 10 instead of squaring 6. And it will make a change. It's not going to be the same answer. 1/3 of 6 is 2. 2 times 100 is 200. We get 200 pi here. 200 pi, what was it, cubic centimeters of volume. Compare that. This isn't the answer. We still have to figure out the rest. But compare that to the 120 pi, right? It's a little bigger. Now, that's not the final answer. They asked for how long would it take. We divide this by 45, right? So this time is 200 pi over 45. And that's going to equal about whatever, a little bit more. I'm going to venture a guess, a little less than, probably in the 14s. So 200 pi over 45, 13.96. So 13.96 seconds. Now, you're probably asking the question, and this is what part D is. Explain why you can claim the time calculated in C is greater than B without you doing any calculations. So, now we did do calculations, right? We're not going to say, oh, because the volume's more, because we know that now. The 10, when the parameters change, so the radius, which gets squared, takes the original height and vice versa, you are obtaining more volume. You obtain more volume because you are squaring a larger number. I'll just say that. You are obtaining a your volume is larger. Volume. Your volume is larger because you are squaring a larger number. See, that's the thing. When you think about it, what ultimately happened? You might think, oh, we just switched numbers. No. When you do the volume, and listen, we can rewrite this to kind of look the same, right? The first one is volume was 1/3 area of base, pi times 6 times 6, pi r squared, times height. This other one is volume 1/3 area of base, pi times 10 times 10, times 6. What's the difference? That. Well, I don't know how to put that best, but these 10s are the same, these 6s are the same. This is 5/3 the amount that was. And that's what happens, literally. That's the difference on those ones. Okay, that's number 12. We're a half hour in. Jeez, I thought I was, oh, we'll see if I finish within the hour. Number 13. That's exciting information. Number 13. A water bottle in the shape of a cylinder has a volume of 500 cubic centimeters. So milliliters, right? The diameter of a base, this base, I suppose, is 7.5 centimeters. What is the height of the bottle? Justify your answer. All right, well, the height, diameter. Diameter is 7.5 centimeters. As we know, volume is area of base times height. This area, this base is pi r squared. It is a cylinder, so we have a circle. That means we need to find out the radius. Half of 7.5 is 3.75. So we have 3.75 centimeter radius. We need to know the height. We have the volume. Was it 500 or 500 pi? Just 500. So our volume is area of base times height. So to find height, we got to work that out. Now, I don't know 3.75 squared. I honestly shouldn't care if I just wanted to do the full calculation in the end. But alas, I'll get it done. 14.0625. So height will divide 500 by 14.0625 pi. Now, when I use the calculator, you have to remember that pi has to go in parentheses with the denominator needs parentheses if I do this in one calculation. So 14.0625 pi in parentheses divided. We're getting a height of about 11.32 centimeters. I'm always hoping for something that looks really clean because I feel a lot more validated. It's like, it's at 11.000. I feel like that's what they meant to say. Now I always question whether the answer is right. That's my justification, though. As long as it was a cylinder. And as long as 7.5 divided by 2 is 3.75. Sometimes I can't trust myself. Let's just be sure. I don't know what's going on sometimes. Divided by 2. Totally. All right, number 14. Number 14, find the area of a dodecagon with a side length of 9 inches. So, dodecagon is 12 sides. The side length of each thing is 9. That means that when we're looking at, like, say, the bottom of it, and I always draw it like that to get used to it, because we have to find the apothem. It's all about central angles, apothem, stuff like that. Side length is 9 inches. That means half of that when divided is 4.5 inches right there. We have to find this apothem. This is going to be the same thing we did in previous ones. The central angle, the entire thing right here, is 360 divided by 12. We're going to divide that number by 2. Now, 360, 1/2, I never write it this way, but I'm going to right now. 1/2 of 360 over 12. 360 over 12 is 30. Half of 30 is 15. So 15 degrees is what goes there. Now, in the last problem that we had with the hexagon, we had a 30, 60, 90 triangle. It's a special right triangle with special ratio relationships. This time, we have to use trigonometry to find the apothem. And the apothem we do need to find. Perimeter, we can, let's just do perimeter now. Perimeter, 9 inches per side length times 12 sides total is 108 inches in total. So we have the perimeter, but the apothem is set up using trig here. Opposite and adjacent are known or used according to the 15, and tangent will therefore be what we have. Tangent of 15 degrees equals opposite over adjacent. So you multiply both sides by a, divide both sides by tangent of 15. You get 4.5 over tangent of 15 degrees. So the apothem, you know what? We'll leave it as exact. I won't round it right now. So your whole area of this dodecagon is 1/2. I don't know what that's doing there. 1/2 apothem. You know I'm going straight to the calculation probably. Actually, you know I want an exact answer to write out first. Apothem times perimeter. Because I can do half of 108, 54, and multiply it by 4.5, whatever that is, 243. So we get 243 over tangent of 15 degrees. Now make sure your calculator's in degrees, because mine always resets to radians. I guess I said it earlier. 243 divided by tangent of 15, and I'm getting 906.888. So 906.89 square inches. Yeah. Is that what they wanted? Yeah, the area of a dodecagon. They should have said regular dodecagon, by the way. I should call them out on that. Last one from the Chapter 11 test before we hit cumulative reviews, number 15. In general, a cardboard fan with a greater area does a better job of moving air and cooling you. I agree. The fan shown is a sector of a cardboard circle. Another fan has a radius of 6 centimeters and an intercepted arc of 150 degrees. Which fan does a better job of cooling you? So we, what do they say? With a greater area. So we got to find the area of these two things here. We have the 120 degree one with 9 centimeters. It's basically sector stuff. Whatever 120 is out of 360, 1/3 by the way. If we call this X, this sector area X is out of the area of the entire circle. That would be a pi r squared. I hope you can see that 9 there for the radius. That would be the radius. Remember, that's the radius of a bigger circle, right? Radius of a bigger circle, and its radius is 9. This is one of them. 120 over 360 is 1/3. I totally want to dig into that. And this is 9 squared, so 81 pi. We're going to multiply both sides by that. So X is 1/3 of 81 pi, which is 27 pi. This is in squared centimeters. Now, I have no need to round. They're asking which fan does a better job of cooling you. I just need to compare the areas. The other one is going to be something else in terms of pi, unless it kind of gets like bad numbers. I'm probably not going to round. We'll see. Let's do another one that we call Y. Okay, so we'll use the other one, 150 degree. Ooh, maybe not as pretty of a number. 150 out of 360 is something. That's the same as Y out of this 6 centimeter radius. I'm going to guess this one's going to work more. That 9 squared is really going to take its toll in like assisting a lot. I believe a lot. Yeah, significantly so. Totally. So, yeah, the first one. Anyway, let's figure out what this is. That's 36 pi. And 15 out of 360, 5 out of 12. We're going to take 5/12 of 36 pi. 36 divided by 12 is 3 times 5 is 15. 15 pi square centimeters. Not only is that first fan, I just want to call it the first one, the 9 centimeter radius with 120 degree, central angle? What do they call that? Intercepted arc. Intercepted arc fan will do a better job of cooling you. Not only is that one bigger, it's almost twice as big. Or twice as effective at cooling you. I don't know if that's what they mean. See, they never said that it's proportional to how much it cools you. That if it has twice as much area, it'll cool you twice as much. That's not necessarily true. But just the more that it is for sure. All right. Guys, that's it for the Chapter 11 test. We're going to move into the cumulative assessment portion, which has 9 more questions that can range anywhere within any of the previous 11 chapters. I have no idea which. Based on the Chapter 10 one, they're probably still going to overload some of the Chapter 11 stuff. And, yeah, we'll go ahead and see what it looks like. So, without further ado, guys, let's move forward to that one. If you have to download that PDF, it's in the description section below. I made them 2 separate PDFs. Away we go. Number 1. The directed line segment RS is shown. Point Q is located... Oh, I almost forgot how to do these. Point Q is located along RS, so the ratio of RQ to RS is 2:3. What are the coordinates of point Q? Not that I forgot, but I almost forgot that these were like problems to do. So point Q, I don't know, maybe it's somewhere like that, right? They said this is some 2-to-3 ratio relationship, like that. In fact, we gotta work that out in some sort of way. It doesn't mean that that's exactly 2 and 3. This could be some 2x and some 3x. What I do forget is how I want to talk about it. I can get the answer, but more so I want to just work out how I want to say the things I want to say. Because I don't believe we're going to use an x there. I'm just giving you where the ratio exists. So here's the important part. It's a 2-to-3 ratio relationship there, but RQ is 2/5 of the way to RS. Or is 2/5 of the length of RS. So RQ to RS is the more important ratio relationship. That's 2/5. 2 over 2 plus 3. Because what we're going to do, what I kind of recall doing, is we want to take 2/5 of this vertical distance, 2/5 of this horizontal distance, and take it away from R's position. Now, R's position is at -2, 5. It's at -2, 5. We have to go down 5 and over, I'll write it right here. We have to go down 5, and we have to go over, it looks like 10, to get to those spots. But what I want to do is take 2/5 of those values. What I want to do is find Q. Q will be at negative 2 is the X. From negative 2, I'm going to add 2/5 of 10. I have to go 2/5 of the way that would have been 10 over. See, I don't know if this is how I wrote it at the time. Apologies if it's way different. From the 5, I have to take away, I'll put a minus. We go down 5. I have to take away 2/5 of 5, right? We're subtracting 5, but we got to go 2/5 of the way there from 5 to get to Q. So Q will be at negative 2 plus, what's 2/5 of 10? 4. And what's 2/5 of 5? 2. So Q is going to be at 2, 3. Now, where did I put it? I put it at 2, 3. Pretty much. I was just spitballing it less than halfway, and I wanted to look at an integer. So Q is at 2, 3. It's going to be answer C. I don't know what chapter that was from. Must have been the similarity chapter? Chapter 8? I don't know. Number 2. In the diagram, line RS is tangent to circle. This is chapter 10. Line RS is tangent to circle P at point Q. And PQ is a radius of circle P. What must be true about RS and PQ? Let me tell you what I know about them. They intersect at 90 degrees. And that's all I know. I don't know what else they're going to say. So select all that apply. Oh, PQ is half of RS. I don't know anything about RS's length. So no idea about RS's length whatsoever. PQ equals RS. I know nothing about RS's length. I have no idea. PQ is tangent to circle P. No. It touches once, but it's not the touch once that we're talking about. If we extended this infinitely, it would touch twice. That's not the kind we're talking about. So I guess this is just multiple choice. I thought it was multiple selection. PQ is perpendicular to RS. Yes, indeed. They create a 90-degree right angle with each other. When I said I don't know what else, I was hoping they'd tell me other things that's true about it. PQ, I'm just going to write that out. PQ is perpendicular to RS. Line RS. Yeah, I know nothing about RS's length. If they told us RS is the same as the length of the diameter, and they didn't, then sure. Okay. Let's go to number 3. A crayon can be approximated by a composite solid made from a cylinder and a cone. Yeah, they're basically saying that you have like, I got this cylinder here, right? And then I'll do it upside down. And then I have a cone like that of the same kind of thing, right? There's a crayon. It's not a perfect one at all. It's just, there's a crayon. Maybe I'll keep it drawn out so I can use the measurements. A crayon box is a rectangular prism. Oh, and then we have one of these guys. All right. The dimensions of a crayon and a crayon box containing 24 crayons are shown. Find the volume of a crayon. Find the amount of space within the crayon box not taken up by the crayons. So here's what we're going to do in a logistics sense. Once I find the volume of the crayon for part A, in part B, I'm going to multiply that by 24. And I'm going to take it away from the volume of the box. Because whatever's volume of the 24 crayons taken away from the volume of the entire box is all the empty space. So let's start with part A, finding the volume of the crayon. They give us a cylindrical height of 80, let's call this object 1, of 80 millimeters. When they say D is 6 point, it's a smaller, it's a smaller cone. It's not the same as this thing here. They actually, I thought they were going to approximate it like that. This cone has a smaller radius, has a smaller circle than the cylinder. So R1, D1, diameter 1 is going to be 8.5 millimeters, whereas diameter 2, this guy, because this is going to have its own different height and stuff, diameter 2 is 6.5 millimeters. So, and the height of this one here. Oh, is that blue? Sorry, I thought it was black. The height of this one here of object 2 is 10 millimeters. Okay, so for part A, the volume of the total, look, I'm going to go like to the point pretty much when it comes literally. We're going to add these two. So we have volume 1, area of base. Oh, we have to divide. Sorry, I need to write some things out still, actually. Let's do a little bit more. Radius of object 1 is dividing this by 2, which is 4.25 millimeters. The radius of object 2 is 6.5 over 2, which is 3.25 millimeters. They look closer to each other than I thought. So the volume of the total is going to be, and listen, I'm going to be pretty straightforward with it. We're going to take area of base times height for the volume of the cylinder. The area of the base is pi r squared times height, 80, plus the other one is a cone, 1/3 area of base, pi r squared times height. Like that. If I typed everything in the calculator right now, I'm actually, I'm so often doing the whole, let's get an exact answer. Let's just type this in the calculator right now as it is. Let's try that out. Let's do, even if they're in terms of pi and we can work all that out, let's just go straight from here. Let's clear this out and make it look easy. So pi, because this is something you can totally do. 4.25 squared, not like so simple you can do it. I'm saying this is something that you should totally take advantage of. As long as you don't mess anything up. Plus 1/3, and I know my order of operations, that'll work itself out just fine. 1/3 pi, that's fine. 1/3 pi r squared. I'm just trusting I type everything right, that I calculated everything before right, and that I treated this thing the way it was supposed to. Times 10. Everything here gets you your volume of, you know what the one thing is that I might regret doing? And actually, let me divide by pi really quickly and see if that's a clean number. Oops, I just typed pi. Shoot. Let me do that again. This whole thing divided by pi. I know this looks really crazy now. It's not clean because we had to divide by something. We had to divide by 3 somewhere. So let's get that clean number again one more time. Clean number one more time. Okay. So this number, remember, is the one we have to multiply by 24. We do have a rounded value, sure, of 4650.21. Maybe this is the time that I wasn't supposed to get the rounded value so much, and the exact answer would have been more preferred. So I have a rounded value of this for part A, right? Part B, I need to multiply this by 24. So 24 crayons approximately equals, but I'm not going to take this number. I'll take the exact one I still have in my calculator. So this one I can do times 24. It takes the previous answer. They said 24 crayons. Sure, I'll round this one because the most I'm going to do, I should say, 079, I'm going to write 08. The most I'm going to do off this is subtract it off what's probably going to be a whole number. That's not really going to do much to my overall. 24 crayons has that much volume. Let's find the volume of the rectangular prism that is the crayon box, which should be more than this, right, to get empty spaces and overall. So the volume of the box, listen, it's a rectangular prism. We do area of base times height. If I want my area of base to be the length times width here, okay, that's fine. Area of base. The height, I'll make 94. So this, that's an exact value. We'll do 71 times 28 times 94. This is 186,872, more than the other number. 186,872. So cubic millimeters. So the volume of the space, the empty space, we're going to take that number minus that number. And it's okay to use the rounded one here because we're still going to round by the exact same amount. This is exact, and that's a single rounding through subtraction. Totally okay. So I'll take one minus the other. The only problem is I don't know how to type that out. Let's see. 18687. No. Previous answer. Minus 1116. Sorry about this. 105. Okay. We're going to get 75. Still rounded though. 75266.92 cubic millimeters of empty space. Sounds like a lot. But when you compare it to this, it's less. Seems like the reverse would be for a potato chip bag, though, right? This is how much potato chips you get. This is how much empty space there is, like that kind of thing. All right, so maybe it's a lot, maybe it's not. I don't know. All right, let's go to number 4. Are we nearing that hour mark yet? I probably won't beat the hour. I got 6 more questions and 10 more minutes. The graphs of f of x equals absolute value of x and g of x equals absolute value of x plus k are shown. Find the value of k. This one will go pretty fast. This, I think, is from chapter 1. I think it's probably from like one of the first sections. This is shifted 4 units to the left. The parent function is shifted 4 units to the left. That would give you a k value of 4. And it'll actually look like, literally, your equation would look like g of x equals absolute value of x plus 4. Yes, that does give you a vertex of negative 4, comma 0. I'm not going to spend too much on that stuff. So your k value is 4. Your k value is 4 in that situation. Well, that's a fast problem. Let's keep moving forward. Good old cumulative assessment. I think that was chapter... Not only do I think that's chapter 1, I literally think that might have been the first section. Or second section. I can't remember what it was now. Number 5. The top of the Washington Monument, Washington, D.C. is a square pyramid. Called a... Oh. Pyramidion? Pyramidion. What is the volume of the pyramidion? So it's a square pyramid. That means when you see a base edge of 34.5, then the area of your entire base will be squaring that 34.5. Whoopsie. 34.5 squared. Let's get that exact value. It's going to be really close to 1200 because 1225 is going to be the square, 35 squared. So 1190.25 square feet. Now the height of this thing is 55.5, and yes, we're doing vertical height based off that to what would be the apex. So the volume of this thing is 1/3 that area of base times height. And I doubt for a second that that would be divisible by 3, so I'm going to go straight into this. So times 55.5 and divided by 3. Excuse me. I think this number is exact, so I'm going to write out, and I'm glad it's multiple choice to reassure that I feel like I'm probably doing it right. There's probably one where you're not dividing by 3. That would be the wrong answer, but I didn't calculate it. 22019.625 cubic feet is what I'm getting out of this thing. I'll see if that's one of the answers. So I'm guessing there's probably an answer here as well. That's probably like times 3, 660 whatever, 559 or something like that. This one, right? That's wrong. That's wrong. But that's the one if you don't take 1/3 of it. So it's going to be this one here. I didn't round, but it's going to be that one there. Okay. Excuse me. Number 6. Prove or disprove that the point... Well, it's not an actual proof to me. That the point 1√3 lies on the circle centered at the origin and containing the point 0,2. So a circle containing the point 0,2 centered at the origin. Let's get like a rough drawing of that. Centered at the origin, it contains 0,2. That means the radius is 2. Centered at the origin, that means you have an HK of 0, 0. That means this equation is x squared plus y squared equals 2 squared, or x squared plus y squared equals 4. We have to see, if I plugged in 1 for x and √3 for y, does 1 √3, is that a solution? If I plugged in 1 for x and √3 for y, do I get a true equation out? Does 1 squared plus √3 squared equal, I was about to say 4 squared, equal 4? 1 squared plus √3 squared equal 4. 1 plus 3 is 4. 4 equal 4? Yes, 4 equal 4. So, yes. Yes, 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 it is true. Oh, they said prove. Oh, yeah, proved. I thought they said prove that it was going to be true. So, there it is. It works out. Number 7. It's a proof. I almost escaped the proofs. Enter the missing reasons in the proof of the base angles theorem. Well, one thing that's going to satisfy me is I'm going to copy and paste this thing so I don't have to write out the statements and reasons. I do have to write out reasons, but I don't have to build the whole table. So, prove, this looks like a basic, this looks like a CPCTC proof, actually. So, maybe I will finish in the hour. Number 7, given that, and it's already marked, given that AB is congruent to AC, that's actually, I'm going to write that as given right now, that's statement 3. Prove that angle B is congruent to angle C. Oh, totally. This is true. Prove the triangles are congruent, and then use CPCTC to prove the rest. So they give you a standard triangle ABC and they ask you, hey, draw an angle bisector here. Draw one. And by definition of angle bisector, those angles will be congruent. They marked it. CAD is congruent to BAD by definition of angle bisector. That's totally how they work. Definition of angle bisector. That's what makes it true. DA is congruent to itself. That's this middle guy right here. That'll be the reflexive property of congruence. It's a shared side. And then these two triangles are congruent by side angle side. I got a side angle side congruence theorem set. And therefore, these two angles, once the triangles are congruent, any two angles that correspond to each other, B and C correspond, they're the last letters in the statement, they'll be congruent by CPCTC. That's it. That was a quick proof. I love that one. I don't know what chapter that's out of. I'm missing my chapter 6. I think chapter 6. All right, 2 more questions, about 4 more minutes for the hour mark. What can I do? Number 8. The diagram shows a square pyramid and a cone. I feel like this is going to be a long one. Both solids have the same height h, and the base of the cone has radius r. According to Cavalieri's principle, the solids will have the same volume if the square base has sides of length blank. Well, the idea is the whole area base times height. If they share, they said they have the same height, so they need to have the same area of base. So we see that there's a radius of r for the other one. So if the area of the base is pi r squared, basically for one of them, the other one also needs to be pi r squared. So the solids will have the same volume if the square base has sides of length, whatever. The base of the other one, if I call it x, right, because I just need to find some length of it, this is also x. So the area base of the other one is x squared. I need x squared to equal pi r squared, which means if I take the square root of both sides, I get the length of a single side. X will equal the square root of pi r squared, which is equal to r times the square root of pi. That's what I need for each side length to be, for that one to pan out, to get the same area of the base as the other one as you multiply by height. I guess it wasn't a long problem. It just seemed like something, it seemed like a frustum problem, if you know what I'm talking about, from sections 11.5 and 11.6. The last question we have is number 9. A triangle has vertices of x, y, and z. Your friend claims that a translation of this and a dilation by a scale factor of this will produce a similarity transformation. Do you support your friend's claim? Explain your reasoning. Yeah. I don't know if I have to do it. I have the graph things right here if you want me to do that. I think it's going to get a little bigger than the graph stuff itself. But sure, it's similarity transformation as long as everything stays. Totally. X is at negative 2, 2. Y is at 1, 4. Why not? And Z is at 2, negative 2. Now, they're asking us to do a couple things to this. Let me use my line tool. And I'm still forgetting if this is out of, I guess, chapter 8. So X, Y, Z. So they're saying, all right, take this thing, copy and paste it, of course. Copy and paste it, change its color. Yeah, totally. Let's do the following. X plus 2, 2 units to the right. Y minus 3, boom, boom, boom. And they said, dilate by a scale factor of 3. Now, the one thing that I'm curious, I guess that means from the origin. So that means everything's going to be tripled from here. So I'm going to copy paste it one more time. I'll make it, I don't know, purple. Everything's scaled from the origin. So everything will be 3 times bigger, sure. But it's 3 times bigger in the sense that X needs to go, and I don't know how to make this dilate perfectly, but X is going to go there. Y is going to be 3 times bigger as well. I guess this isn't proper then. How do I make it 3 times bigger and know that I made it 3 times bigger? I'm going to estimate it first and see if it looks right. I think it needs to be a little bigger than that. 1, 2. Let's try that. So if I place X now at 0, negative 3, I'm tripling its distance there. Does Y go? I'm at 3, 1. I need to put it at 9, 3. I probably made it a little too big. Or these points aren't exactly how I want it to be. Probably like that. And then Z would be at 4, negative 5. I'm over-explaining something I don't need to do. Z prime, this Z double prime, I guess, if you will, would be at 4, negative 5. 12, negative 15. But these would be primes. These would be double primes. on these guys. I know you can't see Z at the bottom. I'll scroll down. So we have that right there. I mean, they're asking, does it produce a similarity transformation? Yeah. Explain, because it does. I can't remember what I need to say. Yes, because the triangles are similar. Because I'll say the triangles are similar as angles remain congruent as side. Oh, I don't remember what to say here. They're similarity transformations. Literally, dilations and translations are still similar. I don't know how to say that part because I did it and it shows that they are, man. They totally are, one similar to the other. The angles are, well, here, I'll tell you this. The angles preserve congruency. This is triple the length of what it was before. There's nothing that changed when I did that, basically. It's still a similarity transformation. I forget what we say. And that's the problem. And that's how I'm going to wrap this one up, by saying I forget what we say. But guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. If you need to check something else out, check the timestamps down below in the description section, and you can still download these PDFs if you want to try it again for yourself. So that's probably the end of the IM2 textbook stuff as far as the closing chapter. I probably still have some videos to make up for that, and there's never a time that I'm not making more IM2 videos as a whole. So thank you guys, take care, and I'll see you in the next one.